40 pages. One sentence buried near the energy section. And suddenly, fusion is no longer a physics problem in China's planning documents. It's an industrial directive. On paper, the country still can't sustain a net positive fusion reaction in any commercial sense. Neither can anyone else. Even the most advanced experiment, International Thermonuclear Experimental Reactor in France, is still stitching together components that won't fully operate at scale until well into the next decade. And even that timeline is optimistic, depending on who you ask. Yet here's the contradiction that matters. China is placing fusion energy inside a 5-year plan framework. The same bureaucratic machinery that built its high-speed rail network, its rare earth processing dominance, and its solar manufacturing choke points. Not as a future research curiosity, but as a structured industrial pathway. That shift is subtle, almost easy to miss, but it changes the entire game. Because 5-year plans are not wish lists. They are allocation systems. Capital, talent, land use permissions, provincial competition, all of it starts bending toward whatever is written inside those documents. And once something enters that system, it stops being theoretical. It starts becoming executable. Now think about what fusion actually requires. Not just plasma physics, not just confinement breakthroughs. It needs superconducting materials, precision magnet manufacturing, tritium handling systems, neutron-resistant structural alloys, ultra-high-end vacuum engineering. In other words, entire supply chains that don't fully exist at commercial scale yet. And this is where the tension sharpens. The United States Department of Energy has historically approached fusion as a long-horizon scientific bet, funding experiments, iterating slowly, waiting for physics to catch up with engineering. Meanwhile, China appears to be doing something more aggressive, building the industrial stack before the final physics problem is solved. That is not optimism, that is positioning. And it raises an uncomfortable question that doesn't get asked enough. What happens when the infrastructure for a technology is complete before the technology itself is? Because that's where fusion stops being about energy generation and starts being about control of the first viable supply chain when it arrives. There's a quiet detail in China's energy planning language that most analysts skip over. References to pre-commercial energy systems and strategic demonstration zones. That is not lab talk. That is industrial rehearsal. It implies something simple and unsettling. They are assuming failure in the short term, but certainty in the long term. And that assumption reshapes everything. Factories don't wait for breakthroughs. They prepare for them. Standards get written early. Suppliers get locked in years in advance. Talent pipelines are redirected before demand officially exists. So while the world debates whether fusion is 20 years away or 50, China is effectively asking a different question entirely. What does it take to be first when it works at all? Now here's the part that should not be rushed past, because if this strategy is correct, then fusion is no longer a race to ignition. It becomes a race to industrial readiness. And that race starts decades before the first power plant ever connects to a grid. Opinion line. This doesn't look like a scientific bet anymore. It looks like a systems-level industrial preemption strategy disguised as energy planning. Doubt, question. The uncomfortable uncertainty is whether this is foresight or overconfidence in timeline control that physics doesn't actually allow. Prediction. If even one country succeeds in making fusion marginally commercial, the real advantage won't go to the first reactor. It will go to whoever already built the supply chain around it. And right now, that race is already underway, just not where most people are looking. Fusion doesn't fail loudly, it fails slowly. In funding cycles, in deferred timelines, in another 10 years that quietly becomes the default unit of progress. But China's 15th five-year plan is treating that slowness like something to compress, not accept. There's a reason this matters beyond energy headlines. Fusion is not just another power source. It is the only known pathway to energy abundance that breaks the fuel constraint entirely. No uranium bottlenecks, no lithium scaling ceilings, no fossil logistics chain. Just hydrogen isotopes and containment physics that, if solved, rewrite industrial limits. That's why the reference inside China's planning ecosystem is so specific. The language isn't just fusion research. It leans toward engineering validation platforms and system integration capability. That distinction sounds bureaucratic, but it's actually structural. One is science, the other is deployment readiness. And this is where the real divergence starts to show. The United States, through the U.S. Department of Energy and its national labs like Princeton Plasma Physics Laboratory, still largely funds fusion as an experimental frontier. Massive breakthroughs are possible, but the system is optimized for discovery, not industrial scaling. China's approach is closer to what it did with solar panels 2 decades ago. Not inventing the first prototype, but scaling manufacturing until global cost curves bend. There's a precedent here people forget. In the early 2000s, solar technology was still dominated by Western and Japanese research. By the time the world noticed, China had already built the supply chains for polysilicon, wafer production, and module assembly at a scale that collapsed global prices. The breakthrough wasn't scientific, it was industrial timing. Fusion, if it follows a similar pattern, doesn't reward the first lab that achieves net gain. It rewards the system that can manufacture a reactor class reliably when the physics finally stabilizes. Now zoom into something more concrete. China already operates multiple major experimental fusion facilities, including EAST, the experimental advanced superconducting tokamak, which has repeatedly pushed plasma confinement durations into record territory. These are not commercial systems, but they are testing infrastructure limits in a way that looks less like academic experimentation and more like iterative engineering stress testing. And that's the shift most observers underestimate. Because once a country begins iterating fusion devices like industrial prototypes rather than isolated experiments, the learning curve stops being linear. It becomes compounding. Still, there's a catch buried inside all of this optimism. Fusion isn't just an engineering problem, it's a materials science ceiling problem. Neutron flux degradation alone destroys conventional reactor structures faster than most alloys can tolerate. Tritium breeding cycles remain experimentally unstable. Even superconducting magnet systems face scaling challenges when moved from lab-scale tokamaks to grid-scale reactors. So the question becomes sharper. Is China building toward a breakthrough, or building around the assumption that the breakthrough will arrive on schedule? Because those are very different strategies. One assumes discovery leads, the other assumes infrastructure leads, and infrastructure is expensive to pause once it starts. Opinion line. What stands out isn't that China is optimistic about fusion. It's that it's reorganizing industrial policy as if the uncertainty around fusion has already been resolved. Doubt. Question. But I keep coming back to this. Can political planning actually accelerate a physics bottleneck, or does it just create very expensive readiness for an event that may still be decades away? Prediction. If fusion crosses even a partial commercial threshold in the next 20 to 30 years, the advantage will not come from who achieved ignition first. It will come from who quietly built the manufacturing ecosystem in advance, without waiting for permission from physics. And that gap between discovery and deployment readiness is where the next energy hierarchy will be decided. There's a moment in every industrial transition where the real competition stops looking scientific and starts looking logistical. Fusion is hitting that point earlier than most people realize. Because once you move past the headlines, ignition attempts, plasma records, laser compression milestones, what's left is something far less glamorous. Who can actually build the ecosystem that turns a one-off experiment into repeatable hardware? That's where the 15th five-year plan becomes interesting in a way most Western analysis misses. Inside it, fusion isn't treated as a single program. It's embedded across materials policy, advanced manufacturing targets, and energy security language. That matters because it means fusion is no longer isolated inside physics institutes. It's being distributed across the entire industrial machine of China. And when a country does that, it stops asking, can we achieve this? And starts asking, what has to exist for this to already be normal when it works? Now contrast that with the global benchmark experiment everyone keeps pointing to, International Thermonuclear Experimental Reactor. ITER is enormous, collaborative, and scientifically elegant, but it is also deliberately non-industrial. It is a proof of concept machine, not a production pathway. It's designed to answer one question: can controlled fusion release more energy than it consumes for sustained periods? That's it. No supply chain scaling mandate, no industrial clustering strategy, no manufacturing ecosystem built around it. So you end up with a split reality. One model is optimized for proving that fusion works. The other is quietly optimizing for being able to build 100 versions of it if it does. And that difference creates a strategic asymmetry that isn't obvious until you zoom out. Because if fusion becomes viable, even marginally, the constraint stops being plasma physics. It becomes manufacturing throughput. High-temperature superconductors, precision coil fabrication, tritium handling infrastructure, neutron-resistant structural materials that can survive years of bombardment without degrading beyond operational limits. And those are not problems you solve in parallel after the breakthrough. They are problems you either already solved or you wait. There's a subtle signal buried in China's energy R&D structure that reinforces this. Provincial governments are being encouraged to compete for advanced energy demonstration zones. That means fusion-adjacent infrastructure is being incentivized at the regional level, not just centrally planned. That's important because it creates redundancy. Multiple parallel industrial ecosystems experimenting with the same technology stack under different local conditions. It's inefficient in the short term, but it accelerates learning curves in a way centralized lab systems cannot replicate. Now, here's where things get more uncomfortable, because there is a historical pattern this resembles. In semiconductors, the countries that dominated weren't always the first to invent transistor physics or integrated circuits. They were the ones that industrialized lithography, yield optimization, and supply chain depth at scale. Fusion might follow the same logic. Not a single breakthrough moment, but a slow transfer of advantage toward whoever can turn possible into mass-produced. Still, there's a major uncertainty here that no roadmap resolves cleanly. Fusion requires breakthroughs in multiple domains that are still independently unstable. Plasma confinement stability over long durations, material survivability under neutron bombardment, and economically viable tritium breeding cycles. Any one of those failing at scale can stall the entire system indefinitely. So even with aggressive industrial planning, there's a hard question sitting underneath everything. Can you industrialize something before you fully understand its constraints? Or does industrialization itself assume a level of predictability physics hasn't agreed to yet? Opinion line. The most striking part of China's approach isn't confidence in fusion. It's the willingness to treat uncertainty as something you can organize around rather than wait to eliminate. Doubt, question. But I'm not fully convinced this strategy bends the timeline of fusion itself, or whether it just creates the world's most advanced readiness program for a technology that may still resist deployment for decades. Prediction. If fusion does arrive in a commercially relevant form, the first decade won't be defined by who built the reactor. It will be defined by who already controlled the factories that make the reactor possible. And that's where the real race has quietly shifted, away from physics and into industrial inevitability.